Good morning, everyone. Happy Friday. I don't know, I'm recording this on Tuesday evening. I don't know if I've marked your exams from yesterday's class, Thursday's class, or not. If they're not in Power School, you might have to wait a day or two. They might not get put in until either late tonight or sometime tomorrow, sometime Saturday, April 23rd. I apologize for that. We're going to move on today, and you've already been provided by the substitute teacher the Unit 5 handout, which is dealing with exponential and logarithmic functions and equations. We're going to dive right in here and look at Lesson 1, which is 7.1, and it deals with exponential functions. In this unit, we're going to be dealing with Chapter 7, which is exponential functions and exponential equations, and we're also going to be dealing with Chapter 8, which involves logarithmic functions and logarithmic equations. And I would say at this point in time, many of you might have a conception about what an exponential relationship or function is, but I would guess that nobody, I don't think, understands anything about logarithms. Today what we're going to be doing is analyzing graphs of basic exponential functions and beginning to solve problems involving exponential growth and decay. Problems that involve exponential growth and decay, as we work through this first chapter, are going to get progressively more and more difficult as our abilities get better and better. So the ones we look at today will be fairly basic. To begin with here, there's a definition of an exponential function. It's a function whose equation is written in the form of y is equal to c raised to the x. Now, there are variations of that. It's not always going to be that simple. But in this function, y equals c raised to an exponent of x, I think it's worthwhile to note that x is in the exponent. That's what makes this an exponential function. X is part of the exponent. You're given a statement here about what c is, and there's a lot going on here. It says c is greater than 0. So the base of this exponential function has to be a positive number. It cannot be 0 and it cannot be negative. It needs to be greater than 0, except that c cannot be equal to 1. And if I were in front of you right now and not recording a video, I might explore with you a little bit as to the reason why c cannot be 1. But let's just not worry about that right now. X is a variable. Here's what c can be. C can be a number between 0 and 1 or greater than 1, but it cannot be equal to 0 and it cannot be equal to 1. A few examples of exponential functions. F of x equals 1.35 to the x. That's like saying y equals 1.35 to the x. Y is equal to 2 raised to the x. N of t is equal to 1/2 raised to the t. Let's take a look at an example. Graph each exponential function and then determine all of the following features. So we are going to graph the exponential function y equals 3 to the x by using a table of values. And I'm going to start off with x being 0. So that would mean that y is 3 to the 0. Well, we know that any number to the 0 other than 0 is 1. If I go to x equals 1, the value of y will be 3 raised to the 1. Well, 3 raised to the 1 is 3. If I look at x equals 2, y will be 3 to the 2, which is 9. And I want to point something out to you, and this is very important. This mathematical relationship throughout this unit is crucial in terms of you understanding it. When x increases by 1 each time, y multiplies by 3. And that multiplication of y regularly by 3 is connected to the equation because the base is 3. This 3 here that we're multiplying by each time is because the base is 3. And I think, many of you see why this is the case. If it's 3 raised to the x, every time you increase that exponent of x by 1, you get an extra multiplication of 3. 3 squared means 3 times 3. 3 cubed, which is 1 more for x, 3 cubed means 3 times 3 times 3. So there's an additional 3 there. What that means is if you go in the opposite direction, we should be able to divide by 3. And we can check that out. If you take this and divide by 3, you get 1/3. If you take that and divide by 3, you get 1/9. And we can certainly show that that's the case. 3 to the negative 2 is 1/9. Because everything about exponents in this unit is important. Because 3 raised to the negative 2 means 1/3 raised to the positive 2, which is 1/9. When x is negative 1, this would be 3 raised to the negative 1, which would be 1/3 to the positive 1, which is 1/3. So let's plot these points now. I don't think this is really important that you have this information written down, but I did want to show it to you. So let's see. I'm going to start in the middle when x is 0, y is 1. So we have a data point there. When x is 1, y is 3. When x is 2, y is 9. When x is negative 1, y is 1/3. And I'm a little hesitant to try to plot this point. I could do it, but I am going to have to plot a point over here at negative 2. I am going to have to plot a point over here at negative 2 that's 1/9 for y. And that's so close to the x-axis that I don't feel comfortable drawing it. But I want you to understand that if I chose x equals negative 3, then we would have 3 to the negative 3, which would be 1/27. As I move in this direction x-wise, as I look not at negative 1 or negative 2, but negative 3, negative 4, negative 5 for x, y is going to be getting smaller and smaller and smaller and smaller. And you can certainly feel free to try this with large values of x. For example, on my calculator, if I take 3 raised to a negative, I'm not sure if I said large values of x. What I meant was large negative values of x. So 3 raised to the negative 8. Like, what kind of number is that? It's 1.5 times 10 to the negative 4, which is 0.00015. It's very, very tiny. Hopefully you will understand, though, that 3 to the x is always going to be positive. It doesn't matter how small x becomes in the negative direction. You're still going to get a positive number. And what that means, and you were taught a little bit about this concept last year, but not really a lot. What that means is that as you go to the left on this graph, the graph will get closer and closer and closer. And I'm going to get rid of this point. I really don't like it there. The curve will get closer and closer and closer to the x-axis, but it won't touch. And this is something that we call a horizontal asymptote. So this graph will have a horizontal asymptote. And I know that those of you that are in my calculus class right now have a really good understanding of that. What this function is going to look like, see how good I can do this, is it's going to be a curve which gets steeper and steeper and steeper and steeper. Not bad. I'm going to adjust this slightly. And I don't really care what kind of artist you are. I need you to know that this is what the graph looks like. Some important features of it. So I'll give you a second to finish sketching it. And again, do your best. Doesn't have to be perfect. So we are asked for an identification of these features. Domain. Well, look at the graph. The graph goes forever to the left and it goes forever to the right. I know that when you look at this portion of the graph, your brain focuses on it going up. But no matter how much it goes up, it is always still going to the right. So what that means is that since it goes to the left and the right forever, the domain is the domain of all real numbers, or, I suppose you could say negative infinity to infinity. The range, while looking at the graph, you can see that the y value is always positive, but it's never zero as well. It's hard to imagine, but that graph will get infinitely close on the left to that horizontal asymptote. There's no real limit to how close it can get, so what we're going to say for the range is y is greater than 0. The x-intercept? Well, there isn't any. That graph never touches the x-axis. The y-intercept is at 0, 1, and the horizontal asymptote is the x-axis, or the line y equals 0. Part of me wants to just say immediately, does anyone have any questions? But I can't travel through space and time at the same time. I can't answer questions if you had them anyway. So throughout this lesson, if you do have questions, make a note of them so that you can get them answered later on. Let's take a look at the next example. Y equals 1/2 raised to the x. So for x equals 0, this would be 1/2 to the 0, which would be 1. For x equals 1, it would be 1/2 to the 1, which is 1/2. 1/2 to the 2 would come next, which is 1/4. I want you to notice that as x goes up by 1 each time, y gets multiplied by 1/2 each time. The significance of that, really important, is that the base of the exponential function is the thing that y keeps getting multiplied by. If you were to take 1/2 raised to the -2, let's see, on scrap paper, 1/2 raised to the -2 means take the reciprocal of 1/2 to the +2, which gives you 4. 1/2 raised to the -1 is 2. We're still multiplying by 1/2 each time x goes up by 1. So we'll plot some points. The y-intercept is 1 again. The y-intercept is 1. It passes through 0, 1. It passes through 1, 1/2. It passes through 2, 1/4. And this is a point that I would be hesitant in actually plotting, but I guess I can put it in there. When x is -1, y is 2. When x is -2, y is 4. If I were to go to -3, y would be 8. And this is what the function looks like. Roughly, that means there is an asymptote here as well. I didn't mention it, but you should draw that asymptote as part of what you present as the graph of the function. It's not actually, I want to just adjust this slightly, part of the graph, but it tells you some information about the graph. So this is what the function looks like. I think this is fairly straightforward so far because we're just learning here about what they look like. What is the domain? Well, if you look at your graph, it extends in both directions horizontally. What is the range? Y is greater than 0. There is no x-intercept. The y-intercept is at 1. And the horizontal asymptote again is the x-axis, which has an equation of y equals 0. So very, very basic introduction here to these functions. This illustrates a significant idea here about the difference between what's called an increasing exponential function and what's called a decreasing. By the way, just like for you Math 31 students of mine, increasing means from left to right. So in calculus, we always talk about something increasing from left to right or decreasing from left to right. This is called an increasing exponential function, and it will happen whenever, everyone, the base is more than 1. If the base is more than 1, like in the first example where I believe we had y equals 3 to the x, the graph will go through the y-axis at 1 and it will increase. On the other hand, if the base is between 0 and 1, then that is a decreasing exponential function. And again, everybody, we're talking about decreasing from left to right. And now what you can do is add some information to that graphic that's on page 1 of this lesson. We can now say that yes, c has to be between 0 and 1 or greater than 1, but if c is between 0 and 1, the function is decreasing. If c is greater than 1, the function is increasing. And I think that's something that you really ought to add to that graphic on page 1 of your handout. All right, let's take a look at example 2. What function is this exponential function? Well, look, when you go from -2 for x to -1 for x, the y-coordinate changes from 16 to 4, which is multiplying by a quarter. When you go from -1 to 0, the new y-coordinate becomes 1, which is multiplying by a quarter. So we're adding 1 each time. And what happens is y gets multiplied by a quarter. So what I've tried to impress on you is that c, the base of the exponential function, is the number that y gets multiplied by regularly. So the answer to this question is 1/4 raised to the x. And we're done. This is too simple to be an exam question. I'm still trying to warm you up to the idea of what c is. C is a base that y is being multiplied by regularly. Let's take a look now at example 3. Well, a little bit of background before we get to example 3. When you have an increasing function, in other words, where c is greater than 1, I'll go back and show that to you. When we have this type of function that's increasing, this is what we often call exponential growth. Think of the word growth. Growth means getting bigger. And in those functions, the quantity of y is getting larger. So this could be investments, values of investments increase, populations of bacteria or people can increase. On the other hand, when you have an exponential function that is decreasing, which means c is less than 1 but bigger than 0, we can call that exponential decay. And this happens with things like you buy a car and every year that goes by it's worth less and less, or radioactive decay, and I know some of you took Physics 30 already, so you're familiar with that idea. So now if you go back to that graphic again and you take a look at the meaning of c, if c is between 0 and 1, it's a decreasing function. If c is between 1 and infinity, in other words, it's greater than 1, it's an increasing function. We can call those exponential decay and exponential growth, respectively. And I would like you to add those terms to that graphic on the first page of this lesson. Or you could add those terms if you wanted to these graphs. This is exponential decay. This is exponential growth. All right. Just a note here, the textbook uses the letter C for base. Your formula sheet is going to use B for base. You have to be adaptable and use whatever letter you feel most comfortable using. I don't like really using B for base because B is a parameter in translations. It has to do with horizontal stretches and reflections. Okay, example 3, a radioactive sample of some isotope has a half-life of 15 days. This means that every 15 days, half of the stuff is left. So I want you to notice that the horizontal axis is measured in 15-day intervals. So this is the beginning. This is one 15-day interval. This is another 15-day interval. This is a third 15-day interval. And if it tells you that every 15 days half of it changes, that means half of it is left. Which means that if you start off with 1 gram, after 15 days you have half a gram, and then you have a quarter of a gram, and then you have an eighth of a gram. So there's a graph shown to you and we're asked some questions. What is the initial mass? Well, the initial mass is 1 gram because that is the value of y at the beginning. What value does the mass approach as time goes on? Well, it's going to approach 0 because there is a horizontal asymptote there. Look, if you keep dividing, and by the way, I just noticed this. I don't know if it's like this on your handout. This should be a comma after the 3. If you keep dividing the mass by a half, you will never reach 0. Now, those of you that have taken Physics 30 with me know that you have to reach 0 eventually, but this is a math class. So we're just going to pretend you keep dividing by 2 each time. So the mass approaches as t gets big. The mass approaches 0 grams. If this were a calculus class, I wouldn't use the word big. I would say infinity. What are the domain and range? The domain is t is greater than or equal to 0. You can see on the graph that t has a value of 0 and it keeps increasing as we go to the right. The range, well, this is tricky. On the one hand, the mass has to be less than or equal to 1, but on the other hand, it has to be greater than 0 because you never reach 0. So another way to put this is the mass, which is the range, is an element of the numbers more than 0 but up to or equal to 1. C, what's the exponential decay model? Well, things are being multiplied by a half regularly, so the mass is 1/2 raised to the t, where t is the number of 15-day intervals. This is just a variation of example 2, except it has a real meaning in the real world. As x is going up by 1, you go from 0 to 1 to 2 to 3. Y is being multiplied by a half. And the thing that you multiply y by is the base in y equals c to the x. So that's why we have m equals 1/2 to the t. By the way, there's nothing wrong with you writing m equals 0.5 to the t. D, how long is it going to take to reach 1/30th of its original mass? Well, that would be 1/30th of a gram, which is going to be a pretty small number. Right? What is 1 over 30? 1 divided by 30 is like 0.03 repeating. It's a pretty tiny number. So the only way for us to really answer this question is to solve this graphically. We already know the equation for the mass. We can put it in for y1, 0.5 raised to the x. I'm going to set up my window settings to kind of fit what I'm looking at on the screen here on the graph. I have to go from 0 to 1 for y. For x, I'm going to go from 0 to, well, I've already got up to 3 for x. Here's x equals 3. Let's go up to x equals 8. It's just a guess. I also need to graph y equals 1 divided by 30. So let's take a look at these now. There's my exponential function that's showing decay. There's my 1 over 30. I need to simply find the x-coordinate of the intersection point by going to my Calculate menu, choosing Intersect. Right now, since I only have 2 curves, I can just pretty much close my eyes and hit Enter 3 times. And I get 4.90689. But that's not the answer, because the question was, how many days does it take? I'm pretty sure it says, how many days does it take? This x value is not a number of days. This is 4.9 15-day intervals. So to answer this question, we need to multiply that x value by 15. If I quit out of here, and hit my x key and hit enter, there's my x multiplied by 15. So the answer to the question is about 74 days. We have one more thing that I want to do here. It looks like we've been at it about a half hour. This next thing should take about 10 minutes. which would mean if my math is right, you will have about 40 minutes to work on the assignment today. Unfortunately, nature does not always follow this exponential pattern. The first thing to note is that when you talk about things increasing or decreasing in value, we don't use x, we use time. What is the value of my car 8 years after I buy it? Well, that means that my independent variable is years, which is time. What is the population of the Earth expected to be in the year 2040? Well, we're going to use a time value in order to determine that population. All of these things are graphs showing time. So if I can go back just for a minute here, I don't want to be too verbose here, which means too blabby. But if you look at an increasing exponential function, whatever is increasing is most likely increasing over time. This is time. If you look at a decreasing exponential function, something is decreasing over time. So that's the first thing to note, is that we take that equation, y equals c raised to the x, and we change it to y equals c raised to the t. Now it starts to make a little bit more sense. There's another issue though. That variable y could be bacteria, it could be radioactive nuclei, it could be the value of a rare painting, it could be the population of mice in an old abandoned barn. But there's another issue here. And it's that most of the time, the y-intercept is not 1. I mean, think about this for a second. If I go back to these graphs, and we'll go to an increasing, let's say that this is population. And t equals 0 represents now. According to this, at the beginning, the population is 1. I don't know of too many situations in the real world where you start off with a population of one item, whether it's people or mice or radioactive decay or radioactive nuclei or anything. You don't often start off with an initial population of 1. But let's imagine that we do know the initial population. Let's say I told you the initial population was, this isn't drawn to scale, 10,000. That means that the graph has to go through that point and be exponential afterwards. Well, there's a very simple way to turn this blue graph into this graph, and it's to stretch the blue graph vertically by a factor of 1,000. So most of the time, the quantity that is increasing or decreasing does not have an initial value of 1, but that's okay. Because if the y-intercept is not 1, we have to change the y-intercept so that it is the initial value of the quantity that is changing. And we just multiply y equals c to the t times some vertical stretch factor. But the beautiful thing about this is that vertical stretch factor, A, is going to be the initial population. If I take the y-intercept that's at 1, vertically at y equals 1, and I stretch it by a factor of A, the new y-intercept will be A, which means that vertical stretch factor becomes the initial population. So, the function now becomes y equals a times c to the t, where y is whatever is growing or shrinking, t is how many applications of the factor of c are occurring. So for example, if the base is 2, t is how many times the thing has been doubled. If c is 1/4, t is how many times the thing has been multiplied by 1/4. A is the initial amount of the quantity, and c is the factor by which it changes. When I say factor by which it changes, I mean what are you multiplying by each time x goes up by 1. So with that loaded into our arsenal, we've got one more example to do. It says in example 4, Allentown currently has a population of 75,000 and is shrinking at a rate of 5% per annum. Annum means annually or per year. Brementown only has a population right now of 10,000, but it's growing at a rate of 9% per annum or 9% per year. So what are the exponential functions for the population of Allentown and of Brementown? We're going to use this, y equals a multiplied by the base raised to the t. A in Allentown's case has a value of 75,000. A in Brementown's case has a value of 10,000. Now, what is the base? And I just realized I used B. I'm going to use C. What is the base? In other words, what is Brementown's population being multiplied by every year? Well, if Brementown is increasing by 9%, that means the base is 1.09. And I'll leave it to you to play around with some numbers, but if you take a quantity, it doesn't matter what it is, maybe the price of a new car, and I tell you that tomorrow they're going to jack the price of that car up 9%. If you take 9% of that price and add it to the current price, you will be finding 109%, which is 1.09. So what's happening here is you have 100%, you're adding 9% to get 109%, which in decimal form is 1.09. In Allentown's case, you have 100% of the population, and at the end of the year you lose 5%. And if you lose 5%, then you're only going to keep 95%. So 100% plus 9% is 109%. Percent means divided by 100. 109 divided by 100 is 1.09. 100% minus 5% is 95%. 95% means 95 over 100, which is 0.95. So what does this mean? It means that Allentown's population, the population of Allentown, is going to be 75,000 times 0.95 raised to the t. Brementown's is going to be 10,000 times 1.09 raised to the t. I want you to notice that for Allentown, since the base is less than 1, it's a decreasing function. So this is decreasing. Whereas Brementown has a base greater than 1, which means this is increasing. One of these is kind of like an exponential decay. The number of people in Allentown is decaying. I'm not saying the people are decaying, I'm saying the population is decaying. The number of people in Brementown is growing, so it's increasing. It's growing, growth. Just before we finish this off, I want to pull us full circle back to the beginning when I said to you that we are going to be looking at applications, and our sophistication of the application understanding is going to grow from day to day. So we're going to continue to work with this type of thing next week. One final question here. How many complete years will it take for population of Brementown to exceed the population of Allentown? Like, think about this. Allentown is starting off at 75K. Brementown is starting off with a population of 10K. But Brementown is increasing at 9% per year. Allentown is decreasing. Not that it's relevant, everybody, but the severity of Brementown's curviness is greater than the severity of Allentown's curviness, because Brementown is growing by 9% per year, whereas Allentown's only shrinking by 5%. What we want to do here, everybody, is find out where these two graphs cross. That's what we want to do. This is Allentown, this is Brementown, and the only way we can do this so far is to use our graphing calculator. You do not know how to solve this algebraically yet. So I'm going to put in for Y1 Allentown, which I believe was 75,000 times 0.95 raised to the x. Brementown is 10,000 times 1.09 raised to the x. I mean, looking at the graph on your screen to the left, our y values have to go up to at least 75,000. So in my window setting, I'm going to go from 0 to 75,000 for y, and I'll go up by increments of 10,000. Determining what to do for x can be tricky. I would just say to you that I don't expect that they're going to meet after 1 year or necessarily even 2 years. It might be up to 20. So there's Allentown declining, declining. People are losing jobs. People are selling their houses. People are moving out. Here comes Brementown. Business is booming. People are moving in. So we can see the point of intersection, and we can find that with the Calculate menu and choosing Intersect. They intersect at 14.65 years. And this next little bit of business is important. We have to round that up. Even if that were 14.1, we would have to round it up because the question says after how many complete years. So you wouldn't round down no matter what in this case. The answer to the question is 15 years. And finally, I can demonstrate to you that we could have solved this using our tables. I could have set up my table. I just hit second window, where I'm about to. Second window to start at 0 and go up by 1 automatically. Go to my table and see that Allentown is decreasing, Brementown is increasing at 12 years, 13 years, 14 years. At the end of 14 years, Allentown still has more people. But when you get to 15, after 15 years, Allentown is lower. So we could have answered it that way. I'm going to be posting the link to this video in our Google Classroom, so if you need to watch some examples again or listen to some explanations again, I would encourage that. For practice problems, this is textbook work on page 342, 3, 4, 6, 8, and 10, I believe. I hope that lesson made sense to you, and I hope that you have a wonderful weekend. We will see everybody on Monday. Take care of yourselves.